Hey everybody, welcome back to Linear Algebra Online. So today I just want to do a few more induction problems, but these ones all with matrices. So we saw, I kind of motivated induction with this problem, that if you have this matrix, then a to the n is this. And I just want to show you kind of how we would go about proving something like that with induction. So base case, we've got, you can just say something like note, a to the first is, 2 to the 0, 2 to the 0, 2 to the 0, 2 to the 0, which is truly 1, 1, 1, 1. And then we're going to assume that a to the k equals 2 to the k minus 1, 2 to the k minus 1, 2 to the k minus 1. And then we show that a to the k plus 1 is 2 to the k, and 2 to the k, and 2 to the k, and 2 to the k. All right. So, pretty straightforward proof here. Just basically, again, we're going to start with this part. So you can just say something like note, a to the k plus 1 is a times a to the k. And by our assumption, this just equals a times, let's just write in what a is. So a, right, is 1, 1, 1, 1. And then a to the k is 2 to the k minus 1, 2 to the k minus 1, 2 to the k minus 1, 2 to the k minus 1. And then if you just do out the matrix multiplication here, right, you would just get that this equals like 2 to the k minus 1 plus 2 to the k minus 1. And you're going to, that's just this times this. And you're going to get that like everywhere, right? So this one times this one times this one times this. And if you just do this thing plus itself, it's just 2 times that thing, right? So really we can just write this as 2 times 2 to the k minus 1. And then this is 2 times 2 to the k minus 1. And this is 2 times 2 to the k minus 1. And so really we're just tacking on another 2 there, right? So then this truly is 2 to the k, 2 to the k, 2 to the k, 2 to the k. And so then, this proves that a to the n equals 2 to the n minus 1 in every component or entry for all n in the naturals. All right, so this one, I would want you to try to, there is a pattern that you can kind of spot with the matrix multiplication here. And then I want you to try to think of how to prove that pattern using induction. So if you pause and try to work through this problem, that would be best. I'm going to go and just jump into it now. So hopefully you've already paused. All right. So if you do like a few of these out, let's just do like a squared, all right? A times a, you're going to get that. And then if you do just a times a squared, all right, you're actually going to get 1. Oh, wait, sorry, I meant 0. And then if you do a times a squared, you're going to get 1, 3, 0, 1. And you probably already see the pattern, but let's just do one more. A to the fourth would be 1, 4, 0, 1. And so you sort of start to see that, like, okay, a to the n might be 1 and 0, 1 for all natural numbers. All right, and it actually is. So we're going to prove it with induction. So base case, note that a to the first is really 1, 1, 0, 1. Yay. Formal proof notation. And then I'm going to assume that a to the k equals 1k 0, 1, and show that a to the k plus 1 equals 1k plus 1, 0, 1. All right. And again, basically start here and just do some matrix multiplication. So a to the k plus 1 equals a times a to the k. Whoa, not k to the k. Then by my induction hypothesis, right, I have a to the k, I'm assuming is just this matrix right here. So I'm going to put in what a is, 1, 1, 0, 1, and then I'm going to multiply it by 1k 0, 1. And if you do that out, right, you get 1k plus 1, 0, 1. And so again, you've got it. Pretty straightforward. And again, like if I was really wanting to write this up, I would add a few filler words in here and not write things like yay. But it just, I want to make sure you kind of see like the style of how these work with matrix problems. So I want to do one more. Really, I want to do this one because it actually is a very famous matrix, and it's if you were in my room, there's actually, this one's so important that I actually put it up on the board in the front, and it's like a very geometric matrix. So I just want to take a second to talk about what this thing is doing. So this matrix right here is a very famous one because it is actually what we call, I'll even specify, so this is a, whoops, that is not how you spell that word, the counterclockwise rotation matrix. And you can kind of see this. So if you plug in, let's say, an angle of 0, okay, then I'm going to call this like a sub 0. Then cosine of 0 is 1, right? Sine of 0 is 0. Negative sine of 0 is still 0. Cosine is 1. And so when we actually write a matrix with numbers like this right here is where like I hat lands, and this is where j hat lands, and we're going to talk about that some more, like after the matrix happens. So basically, this first one I'm just saying is if you don't do any rotation, so an angle of 0, then your basis, well, I haven't really taught you that word yet, but your vectors I hat and j hat just have stayed put where they are, okay? But if I do something like a, and then do this horrible notation, pi over 2, so if you do cosine of pi over 2, right, you get 0, sine of pi over 2 is 1, negative of 1 then is negative 1, and cosine is still 0. And so now, if you think about it, this is where I hat lands after a rotation, a counterclockwise rotation of pi over 2. And you can really see that because this vector is basically rotating up and really landing right here now, right? And also this represents where j hat lands. So if you have, let's do it on a separate one, this was my j hat with 0 rotation. And then as if I plot negative 1, 0, then I land right here. So you should be able to visualize that like I'm basically taking any vectors and I'm not stretching them out or anything. I'm just literally doing rotations like that, like counterclockwise. And if you change around where the negative is, basically you can get the other rotation. But in math, for various reasons, we always like counterclockwise rotation. So that's kind of the standard 2x2 rotation matrix. And there actually is like a 3x3 rotation matrix, but it's a little more complicated, and I don't want to show it right now. It's actually quite a bit more complicated, I would say. But this is all this matrix is doing. It's just rotating vectors around. And so it actually makes sense that induction would pop up here, because if you do like rotations, right, you should kind of be able to like go back to where you started, you know, in a sense. So there's like some cyclic pattern to how this should work. We're not doing some like really weird linear transformation that like would break a pattern. Like it makes sense that rotations should lead to a pattern. So if you go and try to find that pattern, you have to kind of start off by just doing the powers. So a squared is, so if you do like a times a, right, you're going to get cosine times cosine, so cosine squared. And then you're going to do minus sine times sine, which is just going to be minus sine squared. And then for the first row, second column, you're going to get cosine, well, you're going to get minus 2 cosine theta sine theta. And then you're going to get 2 cosine theta sine theta down here. And then if you do the last one, right, the bottom row times the second column, you're going to get minus sine squared theta plus cosine squared theta. And then that might not look like there's a pattern, but you got to use some trig identities. So this and this are a famous, sine 2x identity. So you have in those ones you have gosh, I just did it again. You have sine 2 theta there and sine 2 theta there, right? And then this is also a trig identity. If you just put that over there, that's the way you usually see it. But that's the cosine 2 theta one. So this is cosine 2 theta, cosine 2 theta. And this shouldn't really be surprising, because all we've just done is we've rotated by the angle twice if we do a squared, right? So that's what 2 times the angle is, right? And if you just keep doing it, like if you do a cubed, right, you'll actually get, it takes a while to kind of go in and do, but you would get cosine 3 theta, sine 3 theta, sine 3 theta, cosine 3 theta. And it's easy to kind of start to see, like, again, that makes sense because you're just rotating by theta 3 times, so you would just stick a 3 in there. And that's why this pattern shouldn't be that surprising. The pattern truly is cosine n theta, sine n theta, sine n theta again, and then cosine n theta. And I don't really want to go through the induction here, but I might in like a future video if you guys are struggling with it, but I kind of wanted to leave this one here to see if you guys could figure it out. So it kind of uses like some other cool like trig identity tricks, but I would say try and solve this problem with induction.